Hey guys, just a quick video today. I'm going to try to keep it really short, and then I think I'm going to post a recap of the field theory stuff, maybe the second half of that Brian Cox video that I posted earlier this week. We've been talking about quantum field theory. Modern quantum field theories tell us everything we need to know about the particles that exist in the interactions between them. Last time we also talked about the fact that there is a problem, which is that we have this other theory, general relativity, which describes how the force of gravity works, and these two theories are incompatible. I want to talk a little bit about their incompatibility and why it arises without getting into a whole bunch of technical details, because we're not really equipped to talk about the technical details of either general relativity or quantum mechanics. But think about, I'll give you an example of two games, one of which is continuous and one of which is discrete. By continuous, I mean the game is always happening, the game is always in motion, the clock is always running. Think of something like soccer, right? Once the soccer game starts, the ball is always moving. It's not like American football where there's a play and then another play and then another play, and then the ball is always somewhere. You can look at the game clock and see what time it is, and the game of soccer is continuous. Yeah, it stops when there's an injury or it stops when the ball goes out of bounds. But you can look at a soccer game at any point during the game and you can say what's happening. There's always something happening. Somebody is running downfield, kicking the ball, somebody's kicking the ball to another person. Now think of a game like chess. If you look at the chessboard and don't look at the people, chess is discrete in time. There are moves that happen instantaneously. There's nothing happening between the moves on the board. When I move my rook and you move your bishop, those are the moves, and the game is discrete in time. Obviously, there are things happening inside the players' heads when they sit and sometimes stare at the board for 10 minutes at a time, choosing their next move. But in terms of the playing field of a chessboard, the moves are discrete. They happen all at once in little chunks, little bits. The space of a soccer field is also continuous. You can be anywhere on that soccer field that you want. There are boundaries, but within the boundaries, a person or the ball can be located anywhere. On a chessboard, the space of the universe of the chessboard is discrete. There are only certain places you can be. You can be on A1, A2, A3, A4. You cannot move your bishop to halfway between E4 and E5. That's not allowed. Those spaces don't exist. The space of a chessboard is discrete. It's an 8x8 grid with 64 places that your pieces can be, and they can't be anywhere else. So the space of a chessboard is discrete. The space of a soccer field is continuous. The time chunks of a chessboard are discrete. The moves happen all at once. The moves of a soccer ball are continuous. The ball is always rolling from one place to another. Quantum mechanics is discrete. There are smallest particles that exist that you can't have half of one, just like you can't be halfway between two places, or you can't, you can't capture half of somebody's bishop in chess. The pieces are just the pieces. And the changes that happen on a chessboard are discrete, like the changes that happen in atomic systems. When an electron and a hydrogen atom moves from one energy level to another, that change does not happen gradually. It happens all at once, like a move on a chessboard. So chess is like quantum mechanics. It's discrete, not continuous. But our theory of the space-time of our universe is general relativity. And general relativity treats space-time as continuous. You can be here, or you can be here, or you can be halfway between, or you can be halfway between there and there, or you can be anywhere along a direction in space is a place where you could be. It's like anywhere up and down the soccer field is a place you could be. It's not like chess, where you can only be in the squares. The universe, according to general relativity, is a continuous geometry of space-time. Same goes for time. You can have a certain instant in time, and a second later, or a microsecond later, or a nanosecond later, or a picosecond later, or a billionth of a picosecond later. You can have as small a chunk as time as you can imagine. So what happens when you try to take all of a big massive object and make it smaller and smaller and smaller is general relativity says there is no limit to how small you can make that thing because space is continuous and there is no smallest piece of space. So a black hole can collapse down to a kilometer, a meter, a centimeter, a micrometer, a nanometer, a picometer, and keep going smaller and smaller and smaller. And general relativity allows that because it doesn't put any limitations on how small a space you can have. Okay? Well, if the rules of the very small scale of our universe are quantum mechanics, and if those rules are discrete, that suggests that there should be, just like there's the smallest amount of matter, the smallest amount of energy, when two things trade energy, those trades happen in quanta, these little chunks, these little photons or gluons of energy. If that describes how matter and energy work, shouldn't that also describe how space and time work? If our universe is quantized in matter and energy, why isn't it quantized in space and time? And would that fix the problem of getting a singularity when you try to take the whole universe and squish it down to the size of an atom? In other words, if we had a quantum theory of gravity, which we don't have, okay, but if something exists, modern quantum gravitation, if that existed, and it said, just like matter and energy come in smallest chunks, what if space and time also came in smallest chunks? What if the universe really is like a chessboard? And it is not a continuous space where you can be anywhere, but if you got down to a very small scale, smaller than electrons and quarks. An electron, as it moves through space, is not moving continuously through space like a soccer ball. It is moving from A4 to A5 to A6 to A7 like a piece on a chessboard. That those spaces in between don't really exist. That our universe, both in space and in time, is discrete, made of little tiny chunks, little smallest intervals of space and time. Same goes for time. Just like we experience time as a continuum, as a continuous unfolding of instants down to the nanosecond, one following the other, if space and time really are quantum, then the universe is not continuous in time. It is discrete in time, like the frames of a movie, an old-fashioned movie that came on a long piece of film, and there are all these individual pictures that you show really, really fast, and it looks like a continuous motion. But if you stop the film and look at it very closely, you see, oh, there's nothing happening in between these frames that are, say, a 30th of a second apart. There is no time in between the frames of a movie. The frames of a movie are discrete, not continuous. So when we say that we're after a quantum theory of gravity, what we're saying is we would like the rules of quantum mechanics and the rules of general relativity to be the same. And if quantum mechanics says matter and energy have smaller chunks, then so should space and time have smaller chunks. And maybe if we have that theory, that would prevent these singularities from happening. After all, what is a black hole singularity? It's a finite amount of mass in an infinitely small space. But if space is really quantized, you can't have an infinitely small space. The smallest space you can have is one chessboard square of space and time. Now these squares would be very, very small. There's a very small distance called the Planck length, and there's a very small time called the Planck time. They are trillionths of a meter and trillionths of a second. They're very, very tiny. So these quantum theories of gravity would give us these little chunks, this little discreteness of space and time happen at the smallest imaginable scale. As much smaller than a proton as a proton is smaller than you. In other words, what's the smallest chunk of space? If we go from you down to a proton, that's a factor of 1,000 trillion, 100 trillion, into the 15, 1,000 trillion, quadrillion. So from you down to a proton is a factor of 1,000 trillion. If you go 1,000 trillion times smaller than the proton, that is the scale of the discreteness of space and time that some physicists think might exist. What reason do we have to believe this? Really none. Other than it seems a little unfair that there are three kinds of forces in nature that work this way and one kind of force in nature that works this way, and they don't play nicely together. The other hope is that when we do that, when we create this imaginary quantum theory of gravity that doesn't exist yet, it might give us some why answers to all those things I said we didn't have why answers to. Why are there three families of particles? One interesting thing about there being three families of particles is we live in a three-dimensional universe. 1, 2, 3, up, down, left, right, forward, backward. Maybe those are connected. Maybe there are three families of particles because the universe has three dimensions. Maybe the properties of those particles are connected in some way to the properties of space-time. Is that true? We don't know. That's why we're trying to create this quantum theory of gravity, to see if maybe we get why answers to the things we don't have why answers for right now. So that is the quest in science. If we had a little more time, I would do a video about string theory and try to explain how it is that string theory is a theory both about particles and about space and time and the number of dimensions of the universe. That's a lot to do in the last, it's Tuesday now. We've got Tuesday, Wednesday, Thursday, and then we're pretty much done. So that's a lot to try to do for now. Suffice it to say that all of these new avenues of physics research, these searches for a unified theory, are trying to unify quantum mechanics with general relativity. And one of the things that is a guidepost pointing us in a particular direction is the idea that maybe we can quantize space and time, make it discrete like a chessboard or a movie, as opposed to continuous the way it is in Einstein's theory of general relativity. Will we ever succeed at this? Will we succeed at this in my lifetime, in your lifetime? There's no way to know. But this idea of unification is one that has a very good track record in the history of science, particularly in physics. For example, in the 1800s, we had equations for electricity and we had equations for magnetism. And we figured out that moving electrical charges make magnetic fields, so we can connect those two equations together. And when we did that, we found out that you can have a wave made of electric fields and magnetic fields, and that wave is light. That light is a wave of electricity and magnetism, a wave of electrical and magnetic fields. Well, that means that we have now one theory that unifies electricity, magnetism, and light. That those things were all once thought to be different, and now they're the same. That's an example of unification. Another example has to do with heat. Back in the 1700s, if you ask somebody, what does it mean for something to be hot? I've got a hot cup of coffee here. What does that mean? Well, they would say, well, it's got heat in it, and heat is a kind of stuff. So what's in my coffee is water molecules and caffeine molecules and sugar molecules and heat. And heat was a substance called caloric. That was a kind of physical stuff. That something hot has caloric in it and something cold does not have any caloric in it. Well, that theory was never very effective and it never made a whole lot of sense. Eventually, when people accepted that things were made out of atoms, and you say, what is special about my hot cup of coffee? It's that the atoms and molecules in the coffee are moving really fast. That's what heat is. It's things moving with a lot of kinetic energy on the microscopic level. So there is no extra stuff in the universe called caloric or heat. Heat is a phenomenon of motion. So by the middle of the 1800s, we had unified our study of heat with our study of motion. They're the same thing. And this process of taking two things that seem like different things and showing that they're really the same thing is what we call unification. I can give other examples from what Newton did with gravity, right? Before Newton, if you ask, why does this ball fall? Why drop it? The answer would have been, well, it's made of earth, right? Aluminum comes from the earth, and it's going back to the Earth. I was wrong, but that was people's explanation from the time of Aristotle up through the Middle Ages. If I ask, why does the moon go around the Earth? The answer was, well, because the moon's made of heavenly ether, and it's natural for ether to move in a circle. Hold on. Alexa's telling me I've got a meeting that I'm not going to go to. Alexa, stop. There are downsides to having Alexa on your desk sometimes. What did Newton do? Newton said, no, everything in the universe attracts everything else. The reason the moon goes around the Earth is because of the gravitational attraction. And the reason this ball falls to the Earth is because of gravitational attraction. And those two attractions are the same thing. There's not one kind of physics that works here on the Earth and another kind of physics that works up here in space. That was an example of unification. This gravity and the force that holds the moon in orbit and the Earth in orbit around the sun and Jupiter in orbit around the sun, those are all the same force, unification. So now we've got this theory that says particles behave this way. We've got this other theory that says space-time behaves this way, and we're trying to unify them together into a single theory where the behavior of particles and the behavior of space-time are connected in some way and more similar than they are different. So keep an eye on the news for the next 40 years, and you may hear something about a unified theory that wins someone the Nobel Prize someday and manages to solve this problem. We have not had a whole lot of luck solving it since I was in college and taking the same Astronomy 101 class you're taking back in 1988. We have made very little progress. But who knows? Maybe someday we'll have a unified theory. What we'll talk about next, what I'll do tomorrow, is record a video about what happens as we go back closer and closer and closer to the Big Bang, how these different eras in the history of the universe relate to these different quantum field theories we talked about. In other words, we can go back to a time when there were atoms, back to a time when there were nuclei, back to a time when there were protons and neutrons, back to a time when there was nothing but quarks. And the question is, how far back can we go before the physics as we understand it now, the Standard Model and general relativity, before they don't work anymore? How close to the Big Bang event can we get before it all falls apart?